And the next one is Gert-Jaap.
Gert-Jaap.
Yeah, it's that rolling R, isn't it? Okay, so he's going to talk about the work he's doing with attached, the discrete log contracts. Yes.
Very nice.
Awesome.
Thank you. Thank you for having me here in Berlin. I want to talk to you today about something I think is very exciting, which is discrete log contracts. But before I dive in, let me introduce myself. My name is Gert-Jaap. I work for the MIT Digital Currency Initiative, and I've been working there since April. And the majority of my work is related to layer 2, Lightning Network, and also discrete log contracts, which I'm here to talk about today. So if you want to get in touch, Twitter or email, whatever you like. So a little bit about the DCI for the people that don't know it. It's an initiative from MIT's Media Lab. They have some full-time researchers on staff. They also do research projects with undergrad and grad students. And some of the projects that they work on, obviously layer 2, which is what I'm here to talk about today. And there are some other interesting projects related to digital fiat currency, zero knowledge ledger, ZK ledger, decentralized microgrids, B-Verify, cryptokernel, and decentralized web. If you want to learn more about the other projects, because I'm not going to talk about them today, you can visit the website at DCI MIT EDU. So before I get started about the discrete log contracts, I'll do a small recap about Lightning Network, because it will give you the ability to see how these two technologies are sort of similar. And there was already a lot of talk about Lightning Network, so most of it would already be covered, I guess. So the Lightning Network paper was authored in 2015 by Gert-Jaap and Joseph Poon. It's widely known. I mean, everybody's talking about it or working on it. It's a lot of people involved. And it's being implemented by, I think, 3 or 4 implementations, maybe even more. And there's also derivations of the same setup being implemented for other blockchains. And the core is you have payment channels that update many times. They don't tell the network about what the state of the channel is. And they broadcast the most recent state in order to close or break the channel. And we revoke old states by revealing the private key. So you're basically forfeiting all the money if you publish an old state. Now, discrete log contracts are a little bit different in the sense that they are meant to do conditional payments. So you have a payment that is conditional on an external factor, an external piece of data. And the paper is also authored by Gert-Jaap, the co-author of the Lightning Network paper. And it was published in 2017, so that's last year. And conditional payments, for example, could be if you want to make a bet on tomorrow's weather. So we have 2 people, Alice and Bob. We always call them Alice and Bob for some reason. If it rains, then Alice gets 1 coin. And if it's sunny, then Bob gets 1 coin. Now, the problem is that there's no opcode on the blockchain to enforce this. So there's no op weather. So what you need is an external party that can say it was raining, or that can say it was sunny. Which means an oracle. So this was already covered in, I think, 2 talks back about oracles. I'm still going to call them oracle, even if oracle doesn't like it. So Lightning Network is a very simple script where it's meant to enforce the most recent state. And it uses information that Alice and Bob already know. So they have a payment channel, and they can enforce it with information they have. So they don't need outside information to enforce the channel state. So it's made up of smart contracts, but there's no external state. So if we need external state, like what's the weather, then we need an external party to tell us what the weather is. And not only that, we need to get that into our payment setup somehow, so that if it's sunny, then Bob gets his money. And so the simplest solution would be to have somebody co-sign the payment, so that if Alice and Bob disagree, then there's a third party that can say, yeah, it's really sunny, so I'm going to sign for Bob to get his money. Because if they disagree, so if Alice says, it's raining, I need my money, and Bob says, nah, this doesn't count as rain, I mean, it's just a little rain. Then if they disagree and they made a 2 of 2 multisig, then they're not going to sign the right transaction. And that also puts rich players at sort of an advantage, because if you don't need the money in the contract, then you can say, I'm not going to sign this. And if you're in a hurry, I can give you, half a coin instead of 1 coin, and I'll do it right now. And otherwise, I can wait. So this only works with friends. And in case of money, even sometimes friends doesn't work. So you need an oracle, a sort of third party, a sort of judge to say what happened. They can decide in case of conflict. So you could make a 2 of 3 output, where you say, if Alice and Bob agree that it's sunny or that it's rainy, then they both sign the right transaction, and they don't need an oracle. But if they're fighting, then Bob can say, look, it's sunny, so if Olivia signs the sunny transaction, then I get my money. But there's a problem, because Alice can also ask the oracle, Olivia, to, if you say that it's sunny, or sorry, if you say that it's raining, even if it's not, I'll pay you half a coin. So I get half a coin, you get half a coin, and in the other case, I would get nothing. And the oracle would also get nothing, so they both benefit. So there's a possibility for bribery. And that stems from the fact that the oracle is interactive to the contract. So they decide or co-decide the outcome of the contract individually. So each contract they can influence by saying what the weather was, which means they can equivocate. So even on a day where it's pouring like hell, they can say it's sunny in one contract and they can say it's raining in the other. So it would be better if the oracle could not do that. And it would be even better if the oracle was never aware that the contract even existed. But how would we do that? So I'm going back again to Lightning Network and the state transactions in Lightning Network. So in Lightning, the states are added sequentially, and their validity is enforced by giving private keys away to previous states. So how that looks is like this. Alice and Bob have a channel together worth 10 Bitcoin. Alice has 1, Bob has 9. Now, if Bob were to pay Alice 4 coins, then there is a new state where Alice has 5, Bob has 5, and the previous state is sort of rendered useless by publishing a key that allows either participants to get all the money if the other side cheats by publishing it, which would probably be Bob because he has more money in that state. So if Bob were to pay Alice again, then we have another state and the second state is invalidated. Now in discrete lock contracts, the states are a little different in the sense that all possible states are created up front. And their validity is determined by a signature from the oracle, which is not interactive. So the oracle will publish the signature regardless of it knowing where it's being used. So this is the discrete lock contract for the bet. So Alice and Bob both put 1 Bitcoin into a multisig output. And when it's sunny, Bob gets 2 coins. When it's rainy, Alice gets 2 coins, which is her own coin that she put in and the one from Bob. And if it's cloudy, then we split the pot. So if the oracle signs that it's cloudy, then the only state that is valid, the only one that you can publish to the blockchain to get your money, is the cloudy one. If you publish any of the other ones, the funds are essentially burned or locked. So I'll cover that situation later. So let's look at how this works. The concept is we use the signature from the oracle as a private key. So the oracle has a private key, A, and it publishes the public key, A, which is A multiplied by the generator point. And for each data point that the oracle will publish, it also generates another private key and publishes a public key. So that data point would be the weather in Berlin, Sunday, July 1st at 1 p.m., for instance. So it has to be very specific. It could also be the price of Bitcoin at the last day of the month, 5 p.m., something like that. So using the private keys, the oracle can produce the signature, but using the public keys and the message, anyone in possession of the public keys and the message that's going to be published can calculate the signature multiplied by the generator point, which would be the public key to the signature. And that gives the opportunity for Alice and Bob to pre-calculate the value of the public key to the signature for each of the states that they place their bet on. So they can produce that value for rainy, for cloudy, and for sunny. Which also means that they can create outputs on the Bitcoin blockchain that are spendable if you have that signature. And they use it by combining their own private key with the signature of the oracle. Because you can combine public keys together and then the private keys combined together at sort of public-private key math type of thing. So in the case of Sunny, this would be the state transaction. So there's the input from the multisig, and there's a 2 Bitcoin output that can be spent sent to the public key of Bob combined with the public key to the Sunny signature. And it can be spent by Bob with his private key if he combines it with the signature to Sunny. And similar, there's a transaction for the cloudy state, and there's a transaction for the sunny, rainy state. But then there's the question of how to enforce states, because if it's raining and Bob still publishes the sunny state, then what happens? Similar, if you paid someone money and they publish the old state in Lightning, then you're forfeiting all the money because the state was revoked. Similarly, in this case, if it was raining and Bob publishes this, out of spite or whatever, then nobody has the signature to Sunny because the oracle didn't publish it, and nobody can forge it. And so these funds would be burned. Nobody could spend them ever. Unless there's an extra clause in the script that allows Alice to grab the funds after a time delay. So if Bob publishes the wrong transaction, then nobody can spend it. But after a time delay of X blocks or a day or something like that, then Alice can just claim it. She doesn't need a signature. She can just use her own key and claim the money. Now there's another problem, and that is the trust in the oracle. And I think it was covered in the talk before me as well. If the oracle misbehaves, then this whole system, kind of collapses. So even though the oracle doesn't know about the contracts that are being used, or the contracts in which her signatures are being used, they can still publish the wrong value, either because of a bug in the system or whatever. And if they publish the wrong value, then people's contracts are going to be affected. So you could say, okay, publishing a wrong value, an oracle will lose reputation, and nobody would use it anymore. But there's still, there's still damage to whoever was trusting that oracle. You could also say in the equivocation case, where the oracle says it's raining over here and she says it's sunny over here, if the oracle decides to sign 2 values with the same one-time signing key, then if you have those 2 signatures, you can derivate the private keys. So that's not something that you would do if you're a trusted entity. You could still do it, but it's not a smart thing to do. And for the user in a discrete log contract, it's possible to use multiple oracles to sort of mitigate the risk by combining the signature points together. So if you use 2 oracles, then you can use the 2 signatures of the 2 values, you combine them together. Then you still need a 2 of 3 setup in case there's 1 oracle misreporting, then you can use the other 2. So this was sort of the foundation of what discrete log contracts are and what they can do. We also worked on a use case. So how could you leverage this technology in an actual, real-world example? And what we came to was a forward contract. So traditionally, a forward contract, like on an asset like oil or wheat, is used to sort of secure that you can buy such an asset at a future date for a set price. You actually already have like also Bitcoin, which is future contracts. So you can say that you want to buy a Bitcoin for $5,000 a month from now. And so you hope that it will appreciate and you can still buy it for $5,000. In this case, it's reverse. So the dollar is actually the asset and a Bitcoin is the currency that it's denominated in. So Alice agrees to buy $5,000 from Bob at a rate of 20k Satoshi per dollar, which comes down to $5,000 per Bitcoin on August 1st. So that's a date in the future. And Alice does this because she's afraid of the volatility of Bitcoin. So she has like $5,000 worth of bills to pay, and she only has a Bitcoin, and she's not sure if that Bitcoin is still going to cover the bills that she has to pay. Now Bob expects the Bitcoin to appreciate. So he thinks, if I have to pay her $5,000 for 1 Bitcoin, that's going to be interesting because it's probably worth a lot more by then. And so he agrees to the deal. Now, I was going to actually show this, but we had some trouble with the setup, so we're going to do that after lunch. But we have like a working demo of this concept. So how it would work is we have an oracle, which is Olivia. She's publishing the value of the US dollar measured in Satoshi. So Alice and Bob, they take the public keys from the oracle, and one of the keys is the specific key for the publication that will happen August 1st. They exchange the state commitments, the examples that I showed before, and they both fund a Bitcoin into the contract. So there's like 2 possible outcomes I'll show. So in this case, the dollar is appreciated, which means that Bitcoin became worth less, not worthless, but worth less. So in this case, Alice will still receive her $5,000, which is now 1.25 Bitcoin, and Bob will receive 0.75, which is $3,000. So Bob lost $2,000 while the price of Bitcoin went down with 1. So it's sort of a leverage trade. So here's how it would work. We have the 2 Bitcoin input, the signature to 25,000, which is the rate. Oh, I have this laser pointer thing, which is the rate of the dollar. So Alice can spend the 1.25 Bitcoin, and she still has $5,000, and she can pay her bills. Now the other option is that the dollars depreciated, which means that Bitcoin became worth more. So Alice will receive 0.5 Bitcoin. So she forfeits half a Bitcoin to Bob. Bob now has 1.5, but she still has $5,000, which was the idea of the whole setup. And Bob has now $15,000 worth of Bitcoin. So this is the state commitment for that. So with the signature of 10,000, Alice would get 0.5. Now, when the contract is set up, they sign and exchange all of these transactions before they even fund the multisig output. So they have all the copies, like of 10,000, 11,000, 12,000, all the possible values that the contract can have. And at the time the oracle produces the signature, they pick the right signature, the right transaction, they publish it, and then they claim the outputs back to their wallet. So I'm going to show that after lunch. But there's a couple of things that are not yet done. So this is sort of the first implementation of this, but there's a couple of things that you can still do, the further steps, which is, obviously this doesn't really look like an off-chain solution yet, because we fund a multi-sig output, and then we claim it, and then we put it in our wallet. So that's all on-chain. But if you have the transactions to a discrete lock contract, so you have the funding transaction and you have the state commitment transactions, you can take those out of a 2-of-2 multi-sig Lightning channel. So you can sort of pay the discrete lock contract funding from an existing payment channel. And that means that in case of a friendly settlement, so if everybody agrees and everybody's happy, then you can do a discrete lock contract within a payment channel without ever going to the chain, which is kind of cool. So we're looking into that. The other thing is, right now in our demo setup, the Oracle is an HTTP API. So that's nice, it's still signatures, everything is in order, but the Oracle can just look at the logs and see who used which data point, because it's there. So the whole concept of the Oracle not knowing is sort of broken down by that. So what we're looking into is sort of publishing the announcements and the signatures, the commitments and the signatures of that data in a peer-to-peer fashion within the Lightning nodes, which would be cool. Which is similar to how blocks get replicated over the Bitcoin network. On multi-oracle already covered, given the ability to do 2 of 3 oracles, so that if one misbehaves, you can still use it. And the last one is the ability to sell a contract to somebody else midway, which would involve the other side that remains in the contract to simply re-sign all the transactions according to exactly the same conditions, only with somebody else's key. And that could allow you to, midway sell your forward contract to somebody else. So what we did is we created some materials in case you're interested in leveraging this. We created some tools to run an Oracle that's compatible with the discrete lock contracts. We created a library to interact with the Lightning Network client that DCI is building that has discrete lock contracts as a part of it now. So there's a website on the DCI website related to discrete lock contracts. There's obviously our GitHub, and there's a special mailing list in case you want to get in touch. And I think that's it. So after lunch, we have the demo, hopefully, if everything works. And that's all I wanted to say.
Awesome, that was a fantastic talk. Is there any, yep, there's a question. Here you go.
Thank you. It's a very interesting talk. I read the paper before coming. It's still interesting to listen. So basically, I see the prices of Bitcoin changes every day, and let's say you have the to the fraction of the cent, for example, and you change a few thousand dollars next 6 months, right? So how we can keep hundreds of thousands of the signatures, because you need to generate every single possible cent for both parties to sign, right? So that's create a lot of the overhead, and the if people missing or have a problem with the storage or whatever happened, right? Or you did not capture the price, let's say you bet from 5,000 to 15,000, but go to 20,000. You didn't capture the that state. So how are we going to resolve it in the future? Or you can go to the binary state when you could do the CFD betting.
Yeah, that's a good question. So the question was related to the range of a contract and the amount of signatures that you need. So there's 2 parts to that question. So one is by the limited collateral in the contract, you're also limited to the variation that you can cover within the contract. That's specific to the use case. It doesn't have anything to do with the discrete lock contracts as such. But if both of them put in 1 Bitcoin, then at some point, if Bitcoin drops below $2,500, then Alice gets all the Bitcoin. She gets 2 Bitcoin. But if it drops even lower, it's no longer worth $5,000. So you can fix that by either over-collateralizing the contract, by saying we have to put in 2 Bitcoin each, or 3 or 4. But at some point, you're going to run out of collateral. That's simple. The other thing is the amount of signatures. So one of the things that are also mentioned in the paper, and I didn't want to get into it in the talk because it's somewhat complex, but you could split up the value that the Oracle is going to publish into 2 values. And one could be the exponent of base 2 or base 10, and the other could be the mantissa. And because at some point, all the money is going to go to one person. And instead of having to sign, 100,001, 100,002, you could say everything above 100,000 is for Bob, and everything above 1 million and 10 million. And so you reduce the amount of signatures that you need by splitting it into 2 values. So that's sort of the direction that we're trying to look for the amount of signatures problem. The other simple solution that we actually applied in the demo as well is just to say we're going to round the rate of Satoshi to the nearest multiple of 100. So that if it's 10,100 and not 10,099, so I have to sign 100-fold less different values. That's another option, but it's kind of hacky. So, okay.
Yep. Hello. Nice talk, and thank you for the talk. My question was about what kind of digital signature do you need for doing this nice discrete log contract? And if you can elaborate also in the compatibility of your solution with other blockchains other than Bitcoin.
Yeah. So this uses ECDSA in a Schnorr signature scheme, but it uses elliptic curve signatures. The question if it's compatible with other blockchains is something that we haven't really looked at. So it currently works with Bitcoin or compatible blockchains, but we haven't looked at any other. So it might be interesting research, but...
Yeah, I imagine it's going to work out of the box. That would be my impression.
I wanted to show you how the discrete log contract setup works. So the example I gave for making a forward contract is actually what I'm going to do now. So over here, you see 2 nodes of LIT, which is the Lightning Network implementation that's being worked on at the DCI. We integrated the discrete log contract technology into that, so it's part of it. And this is sort of the preliminary user interface, if you will. So it's a simulated environment. So right now, Bitcoin is worth $5,000. I'm not sure if that's more or less than what it's actually worth. But for the demo, it's worth $5,000. So on the left, you see Alice, and she has a connection to Bob, and on the right, Bob with the connection to Alice. And as we said in the use case, Alice is afraid that the Bitcoin is going to drop. And she has bills to pay, so she wants to hedge against that volatility. And Bob thinks that Bitcoin is going to skyrocket, so he's okay ensuring that $5,000. So what we do is we create a new contract in which Alice agrees to buy, well, let's make it 20,000. $20,000 to 11. Maybe make it 210. Oh, 211. Okay. At $5,000, and I'm going to buy it from Bob. So what this does is at 2:11, which is 3 minutes from now, Alice is still going to have that $20,000, regardless of what happens to the price of Bitcoin. I hope in this demo. So we offer it to Bob, and Bob gets the offer in his screen saying Alice wants to buy $20,000 from you for 20,000 Satoshi per dollar, or $5,000 per Bitcoin. So Bob thinks that's a pretty good deal. So he's going to accept. Now what happens is, if we go to the Block Explorer, that doesn't have any transactions, so maybe I have to mine a block. Yeah, there it is. Okay, so can you see this? That's a bit small, maybe. Maybe I can do this. Makes it better. Okay, so this. Oh, I have the pointer thing. I forget about it. Okay, so this is Alice's wallet. This is Bob's wallet. They both had 5 coins. They spend it into this new script output worth 8 bitcoins, and they get their change back, each of them. So now we have this contract output worth 8 bitcoins. And I'm going to change the value of Bitcoin to 4,000 with the click of a button. If only life was this easy. Huh? So Bitcoin is now worth $4,000. So if we refresh this screen, you can see that over here, the 1 Bitcoin that Alice and Bob had remaining is worth less. Not worthless, worth less. So now, it's still not 211, so I have to wait for a minute and talk a little bit. But when it's 211, the Oracle is going to publish the value of Bitcoin. And that is $4,000 now. And using that signature from the Oracle, we can we know which of the settled transactions will be valid, and we can publish it, and then using the signature, we can claim whatever money is due us back to our wallet. And I'll show that on the chain as well. Because if I press settle now, nothing's going to happen, I guess. No, the value is 0. So we have to wait. Now it's 211. Ah, there we go. So now, the value is 25,000. Or $4,000 per Bitcoin. And there's a signature from the Oracle, which is going to be checked, so it's probably valid. And it will show you that in this setup, we're going to get 5 Bitcoin, and Bob is going to get 3 Bitcoin. And those 5 Bitcoin are still worth the $20,000 that we wanted. So if I settle this, the contract's closed, and then once my publication of the settlement transaction is read by Bob, he's going to claim his part of the money, so then the contract on his side is also closed. And what we can see on the chain is there's 3 transactions happening. So the first one is from the script output. So this is the output that contained all the money in the contract. It's spent to Alice and to Bob. This is minus the fee, of course. And then both of them have to claim back the money into their own wallet to prevent, if the timeout triggers that I said, that if somebody publishes the wrong one, the other party can claim the money after the timeout. So to prevent to prevent Bob from stealing the money back, Alice has to claim the output back to her wallet, so something under the control of her own private keys. And so if we look back in the UI, it's probably updated. So you see that Alice now has 6 Bitcoins, which was the one that she had after the contract was funded, and the 5 from the contract. So even though Bitcoin declined from 5,000 to 4,000, instead of having $20,000, she has, instead of having 20, she has 24. But Bob lost a lot of money because not only does he get less Bitcoin, they're also worth less than before. And that's it.